This lecture series deals with spin-spin coupling, and the spin-spin coupling tells us about the neighboring protons. First, we'll look at the origin of spin-spin coupling, and then we'll see how to interpret and use the coupling information from a spectrum to arrive at a structure. A multiplet arises when a single absorption or peak is split into multiple lines. This coupling, or spin-spin splitting, arises from interactions of the nucleus of interest with the spin of neighboring nuclei. And we use the n+1 rule to predict how many lines an absorbance will be split into. The n+1 rule tells us that if a proton is near n number of adjacent protons, then it will be split into n+1 lines. So as an example, this methyl group that's circled in red, it's next to a CH2 group, meaning it's next to 2 protons. So n is 2. n+1 then is 3. So the signal for that methyl group will be split into 3 lines. It'll be a triplet. And that's what we see in the peak at 1 ppm. That peak arises from the methyl group and it's split into 3 lines. It's a triplet. This CH2 group is next to a methyl, so it's next to 3 hydrogens, or n is 3. That means n+1 is 4. So that signal for that CH2 group is split into 4 lines. We call that a quartet. Finally, the other methyl group here, next to the carbonyl, is next to no protons, so n is 0. That means that n+1 is 1, and so the signal arising from that methyl group isn't split into additional lines. It's a single line, and we call that a singlet. The splitting of a signal or absorbance into multiple lines arises from the interactions of the nucleus with the spin of the neighboring protons. Let's take a look at that and what it means. Let's start by remembering that we're looking at the nuclear spin of a hydrogen in a magnetic field. If there are other hydrogens nearby, then the 2 nuclear spins can interact. And they interact because that nuclear spin generates its own very small magnetic field. So if we're looking at HA here, and there's another nearby proton, I'm calling it HB, then HA feels the applied magnetic field and the added magnetic field generated by HB. If those fields are aligned, then HA feels a greater magnetic field than it normally would because of its interactions with HB. So HA then is de-shielded by HB, and HA will resonate at a slightly higher energy. It will appear slightly downfield. If those fields or spins are in opposite directions, then HA feels a weaker magnetic field. Some of the applied field is canceled by the small magnetic field generated by HB. In this case, HA is shielded by HB and will resonate slightly upfield. These 2 different spin aligned and spin opposed configurations have different energies, and the signal for HA is split into those 2 energies. And that's shown here, where there are 2 lines in the same signal. One line that arises from the spin aligned case, and the other line arises from the spin opposed case. This whole signal is HA. HA is split into 2 lines. It appears as a doublet. Okay, everything we've seen for HA also applies to HB. HB feels the magnetic field of HA. And the signal for HB will also be split into 2 lines, a doublet. One line for the spin aligned case, and the other line for the spin opposed case. So the spectrum will show 2 doublets, one for HA and one for HB. And in those 2 peaks, the spacing between the lines is the coupling constant. It's the energy associated with that interaction of the nuclear spins. And because it results from the interaction of HA with HB, the spacing between the lines, the coupling constant, must be the same in both of the peaks for HA and HB. We call that spacing, or that energy, the coupling constant, and it's reported in Hertz. Because the x-axis of the spectrum has units of parts per million, to convert the spacing in parts per million to the coupling constant in Hertz, we can simply multiply by the frequency of the magnet of the instrument that we measured the spectrum on. We've looked in detail at the case where a hydrogen has one neighboring hydrogen, and this gives rise to a doublet because there are two different spin arrangements, spin aligned and spin opposed, as shown here with the red and blue arrows. In cases where we have two neighboring protons, this gives rise to a triplet because there are three different spin arrangements. And more than that, the intensities of the three lines of the triplet are not equal. Instead, the middle line is twice as tall as the outer lines. We call it a 1-to-2-to-1 triplet. And the middle line is twice as tall because there are two different spin arrangements that give rise to the same energy. Two different spin arrangements that are energetically degenerate, and they account for the middle line. So more generally, the intensity of each peak in a multiplet depends on how many spin arrangements give the same energy. And we can use Pascal's triangle to simplify this process for us. That's shown to the right here. And it shows us that a singlet will have one line. A doublet will have two lines in a 1-to-1 ratio. A triplet will have three lines in a 1-to-2-to-1 ratio. A quartet will have four lines in a 1-to-3-to-3-to-1 ratio, and so on. Now let's try a concept check. Predict the multiplicity of the peak arising from each proton shown in blue. In the first case, that proton has only one neighboring hydrogen, so we would predict it to be a doublet. In the second example, the methyl group is bound to an oxygen, so there are no neighboring hydrogens, and we would predict a singlet. In the last example, the two hydrogens of the CH2 group are next to four other hydrogens. N is 4, so N plus 1 is 5. We should predict a quintet. We'll end this video with the question we saw at the beginning, to determine the partial structure that arises from a single peak. And here we'll be combining what we've learned about chemical shift, integration, and multiplicity. I like to start with the integration, and here an integration of 3 tells me that this peak most likely arises from a CH3 group. The chemical shift of 1.25 ppm isn't very downfield shifted, so these protons are most likely next to an alkyl group or an sp3 hybridized carbon. Finally, the multiplicity. I see 3 lines in a 1-to-2-to-1 ratio, so this is a triplet. That means that N is 2, or there are 2 protons on the adjacent carbon. Another way to say the same thing is that this CH3 group is likely bound to a CH2 group. And that description gives us our partial structure, a CH3 group bound to a CH2 group.